All right, let's go ahead and get started. I want to welcome you again to Unit 8. We're talking about the mole, and we've gone through a number of examples involving empirical and molecular formulas, and I want to just move through a few more examples to kind of make sure that we understand this concept. So let's take a look at this sixth example. It says if bronze is 67.0% copper and 33.0% tin, how many atoms of tin are there in a small bronze metal weighing 12.5 grams? All right. So that's our question. Well, since we're being asked about tin, let's first determine what the mass of the tin atoms is. So they're telling us that I've got 12.5 grams and 33% of it is tin, right? So that means that if I multiply 12.5 by 0.33, the amount of tin is in grams, 4.13 grams of tin atoms, right? So now I know the mass of the tin. So now we'll determine how many atoms weigh this amount. How many atoms weigh 4.13 grams? So we've got 4.13 grams of tin atoms over 1 times 1 mole per, I'm just taking this right off the periodic table, 118.71 grams of tin, obviously, right? So now what I'm going to do is I'm going to cancel this with this. Now what I'm going to do is I'm going to convert to the number of tin atoms. I know that 1 mole of tin has this many atoms, right? I'm going from grams to moles to atoms. This is a two-step process. And when I do that, I'm going to multiply 4.13 times 6.02 times 10 to the 23rd, hit the equal button, and then divide by 118.17, and I get this number. 2.02, three significant digits, I get 2.09 times 10 to the 22nd, 10 atoms. Now you check that on your calculator and make sure that that's correct, okay? So that's the number of 10 atoms. So that's it. It's a two-step process, no big deal, right? It involves a percentage. Some percentage of the bronze was 10, and that takes care of that. So let's move on now to a new topic. I want to talk about percent water in a hydrate. Percent water in a hydrate. What do we mean by that? Well, what we mean is how much of the entire molecule is water. So what is a hydrate? A hydrate is a molecule that contains water, right? It's a molecule that contains water. For example, if we have iron 3 chloride, iron Roman numeral 3 chloride, tetrahydrate, that has a formula of this. It's FeCl3, and then you see that little dot there. That little dot indicates that what comes after is water. Tetra means 4, so tetrahydrate is 4 water molecules. So FeCl3 dot 4H2O, right? So let's do this example. Let's take a look at this one. It says example number 1. It says determine the percentage of water in this hydrate, right? We want to determine by mass the percentage of water in this molecule, FeCl3 4H2O. Again, it's called iron Roman numeral 3 chloride tetrahydrate. So here's what we would do. First, we're going to determine the mass of the 4 water molecules, because there are 4 water molecules, right? That's easy. We'll just say 4 times the mass of 1, which is 18.02, and I got that just by adding up hydrogen twice and then oxygen. And that mass is 72.08 grams per mole. 72.08 grams per mole. Now the total molar mass for the whole thing is iron, right? And there's 1 of those, right? And chlorine, there's 3 of those. FeCl3, there's 3 of those. And then water, and there's 4 of those, we know that. So when we add those all up, what we get is this. We get 234.31 grams per mole. So that's the whole thing. So if we want to know what percentage of water is in this hydrate, what we're going to do is we're going to take just the mass of the water, which is 72.08, and we're going to divide by the total mass, which is 23.31, and then multiply that by 100, and what we get is this number. We get 30.18% water, right? So for this molecule, 30.8% of it is water, and that's called calculation of water in a hydrate. Calculation of water in a hydrate. Okay, make sense? All right, let's move on now. Folks, this one is for pre-AP students only, so if you are not a pre-AP student, you might want to take a break here. We're going to be moving on to something a little bit more challenging. So here we go. It says determine the number of oxygen atoms in 96 grams of carbon dioxide, CO2. How do we do this? Well, the first thing we're going to do is we're going to take the 96.2 grams of carbon dioxide over 1, and we're going to determine the number of moles that is. It's a simple conversion. Grams cancels with grams, and I'm left with grams of moles of CO2. I got the 44.01 by simply adding up the atomic masses of carbon and 2 oxygen atoms, right? So just add those up, it gives you 44.01. And I'm left with moles of carbon dioxide, moles of CO2. Times, now what we want to know is what's the ratio of moles of oxygen atoms to moles of CO2? Well, it's CO2. That means that there's 2 moles of oxygen atoms for every 1 mole of CO2. Let's get that, make sure we understand that. There's 2 moles of oxygen atoms for every 1 mole of carbon dioxide. So, there you go. I'm left now with moles of oxygen atom, right? So now what I want to do is convert that to atoms. So I'm going to multiply that by the ratio of 6.02 times 10 to the 23rd oxygen atoms per 1 mole. That allows me to cancel this with this, and I'm going to be left with oxygen atoms. So I just do the math. I just multiply across 96 times 2 times 6.02 times 10 to the 23rd divided by 44.01, and I get this number 2.6. You check me on your calculator. I get 2.6 times 10 to the 24th oxygen atoms. Okay? All right. Folks, I want to explain a little bit better what I did right there. Okay? I said 2 moles of oxygen atoms per 1 mole of CO2. I want to just talk about that because that's kind of the challenging part of this problem, conceptually. In the same way that a car has 2 headlights, and 1 mole of car has 2 moles of headlights, and so on, 1 mole of CO2 contains 2 moles of oxygen atoms. Okay, so 1 car has 2 headlights, right? So 1 mole of cars would have 2 moles of headlights. Make sense? What about tires? Let's not include the spare tire. 1 car would have 4 tires, and 1 mole of cars would have 4 tires. All right? Does that make sense? Well, the same way, we've got 1 mole of CO2 would have 2 moles of oxygen atoms. So that's where that ratio came from. I just wanted to clarify that. All right. Okay, folks, we're going to go back now to percent water in a hydrate. We've already talked about it. Let's take a look at an example, another example. Be sure to be able to determine the percent water in a hydrate. Let's take a look at this hydrate. We have COCl2.4H2O. That means we've got 4 water molecules associated with the cobalt chloride, right? How are we going to determine the percent water in this hydrate? Well, here's what we're going to do. First thing we're going to do is we're going to calculate the mass of just the water. So remember, 1 mole of water weighs 18.02 grams. So we're going to say 4 moles because there's 4 moles of them. 4 moles is 4 times 18.02. That's going to be a total of 72.08 grams, right? Now we're going to calculate the mass of the whole hydrate, the whole thing, including the water. So we're going to say 72.08 grams, that's for the water, plus 58.93, that's for the cobalt, just got that right off the periodic table, plus 2 moles of 34.45, that's 34.45 for 1 mole of chlorine, but there's 2 of them, it's COCl2, so multiply by 2, and when I do that, here's what I get. I get 201.9 grams. That's total. So if I want to know the percent water, remember percent is part of a whole, I'm going to take the number of grams of water, which we said was 72.8, and divide by the total, which we now know is 201.9. Multiply that by 100%. Here's what I get, 35.7%. So the percent by mass of water in this molecule is going to be 35.7%. All right? 35.7% water in this cobalt chloride. All right? Okay. Cobalt chloride hydrate, I should say. All right, we also need to talk about how to calculate percent composition of water in a hydrate from experimental data. Let's talk a little bit about what happens if we're doing an experiment and how we do that. So let's take a look at this example. We have an orange-colored magnesium sulfate crystals contained water molecules. So these water molecules are in the orange-colored magnesium sulfate crystals. Now, if the crystal is heated and the water is driven off, the remaining substance is yellow and it crumbles, right? It's like a yellow residue or a powder. We want to use the data below to calculate the percent composition of water from the original crystal's mass, right? So what was the percentage of water? So we placed the hydrate onto a flame, and from that we were able to determine the amount of water that was driven off in the process of it heating up, and that's the amount of water, the mass of water, and then we can determine the total mass by simple subtraction. So let's take a look at the data that we've got. So the empty test tube weighs 13.66 grams. The test tube and the crystal before you heated it was 14.58 grams. The crystal before the heating was 0.92 grams, just the crystal, because all we're doing is subtracting this from this to get that number right there, right? And then the test tube and the crystal after the heating was only 14.08. So the water that was driven off is the difference, is the 0.50 grams, right? It's this number right here. That's the amount by mass that was driven off in this heating process. So the only two values that matter are the water driven off, which is, we now know, 0.50 grams. That was a simple subtraction problem, right? Is 14.58 minus 14.08 is 0.50, 0.50. And the crystal before the heating, the magnesium sulfate combined with the water, which was, well, 0.92 grams, right? So those are the only two numbers from this data that I'm really concerned about. So the percent water then is the number of grams of water, experimentally determined, which is 0.5 grams, right? Divided by the grams of the crystal and the water, 0.92 grams, times 100. And that is equal to 54.35%. So in this experiment, what we've determined is that the percent of water by mass of this hydrate is 54.35% water. Folks, that'll do it for this one. I'll see you on the next one. Thanks.